Okay, there's just a few people still getting used to this stuff in Excel, and that WebEx didn't record very well. So let me go through an example of this balloon problem. So what's given is how far to the left one of the cables is, how far up the balloon is, how far to the right. And these are the length of the cable is not the length of the force. Those are two different vectors. They're at the same angle, but they're different magnitudes, they're different lengths. So the first thing I'm going to do is go ahead and just figure out what my angle is based on the dimensions of the rope. So this is, and for this one, if it's 8 high and 8 long, I'm going to get this angle that is up at the top, which if you look at similar triangles, it's also going to be the angle at the bottom here. So this is, if I say tangent is opposite, so the opposite side of that angle is what it's pulled to the left with, and then the adjacent side angle is that height. So I'm clicking on the cells that hold those numbers. So in the future, I could just change those numbers and it would update what that angle is. So there's the angle to the left. Now this does it in radians, so to get that in degrees, I can multiply by 180 over pi, or I can say, please change that cell into degrees. I'm just arrowing over, or I can type in the name of the cell, H5 there. Okay, so there's about 45 degrees on the left-hand side, and I'll do the same kind of thing on the right-hand side. So there's A tan, and the opposite side, that's how far it gets pulled to the right. And then the adjacent side is the height on this thing. Once you have an equation in there, what I can do is just grab the lower corner and pull it down. And that will actually update H5 to H6. So that's kind of a nice thing for Excel. Okay, so I have two angles on that triangle. So I've got this top skinny angle, this bottom angle that is 45, the third angle in my triangle. So all of those have to add up to 180. So I can now get that third angle in here, and for future, I need to use this for sine or cosine or something. So I'm going to go ahead and get everything in terms of radians. Now, there's a couple ways to walk around this. Law of sines might be the easiest. So I have the balloon pulling up, that's the long side, and then the tension on the right pulling down at that really skinny angle, and then the tension on the left pulling down at the other angle. So that ratio of the long side over this angle, let me just get that ratio, and then I can use that ratio to get the tension on the left, the tension on the right, if I have my tension going up. Okay, so I'm going to go ahead, I'll link this all. So rather than typing it in, I'm going to link this all to the table I'm given, so I can go back and change those numbers and it will update it. So if you use these numbers and you get it all to work, you should be able to just go change this and it would work. Okay, so just getting that ratio, so I'm going to say 4,800 divided by sine and the opposite angle. Make sure you get that in radians, not degrees. So that's kind of the ratio of the side to that opposite sine of that angle. And then I'm going to take that ratio. If I want the force on the left, I can multiply that ratio. So the left is going to be times the sine on the right. It's opposite that sine on the right, which was this little guy. And then the right is equal to this ratio times the sine on the left. Make sure you get those radians in. So here's the right is equal to sine on the left times that ratio that we grab. So it's nice to just one way or another grab some cell and figure out the ratio. Okay, we want to prove to ourselves that this is the right tensions here, and it's really easy to block something in here wrong. And so oh, like I got that angle in there wrong. I don't want degrees, I want radians. That looks better, yeah. So the left side should be a much smaller force than the right side. The right side is pulling down. It's in the direction of that balloon. So it should have the right force. Okay, yeah, so it's real easy to just mistype something in there. I'm going to go ahead and let's do method of components to check this thing out. So my force going up, it's purely in the positive y direction. My force going to the left, so this is going to be negative, and I'm going to grab this guy, and we got this angle at the top, so that's going to be opposite. And the angle is right over here, so that's the opposite side of that left angle, and then going up this times the adjacent side of that left angle. And for the right side, we can grab this guy. So now the x direction is positive, and it is opposite. So sine of this angle on the right, that little skinny angle, and it's pulling down. Oh, I need to make the other one pulling down too. Adjacent to that angle on the right. So let me make sure this is pulling down. So the cable is down, 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 and looks like everything in the x direction is equal. So we're good so far. I can pull that equation over. And we have 0 in the y direction as well. So yay! Yeah, so the first thing is to figure out the angles from the dimensions. And then once you have those angles figured out, then you can get the forces from the law of sines. That might be the easiest thing to do. And last step, to make sure you have everything, split it into x and y components and make sure everything adds to 0. It's very helpful to draw a nice big picture, label the angles on that picture. You can see the length of those vectors. That the right side has to be a lot longer than the left side in this scenario. So yeah, draw pictures, drag that balloon to the actual dimensions that you're given so you can see what it looks like. Okay, hope that helps.